All right, good afternoon, everyone. I'm Adam Petcher from the Java Platform Group at Oracle, and today I'm going to talk a little bit about some recent efforts to develop some high-speed implementations of new cryptographic algorithms for the JDK. So first, a little disclaimer, I will be talking about some features that are under development right now and have not yet been released, and we're working on them, but there's no timeline, or we're not even sure if they'll get in at all, so just make sure you guys don't get your hopes too high. I want to congratulate all of you on your bravery for coming in here and coming to a talk with such a scary-sounding technical name. But I want to assure you that this talk is not all low-level cryptographic details. If you're not a crypto expert, that's fine. You can see the crypto composition here is that red part, about a third or so. Most of the talk is just about efficiently adding and multiplying numbers in Java, and that's that blue part. And I've got some benchmarks too. So that should help. Though it will get pretty technical, I'll warn you, but it should be hopefully easy to understand, and it's also pretty fun. The major takeaway from this talk is that we've implemented some new crypto algorithms for JDK 11 and some we're working on for later releases. These use modern techniques, they're new algorithms, they're more efficient, higher levels of security, and a big takeaway is that implementing crypto algorithms 100% in Java can be fast, even when compared to native implementations. So outline, I do need to give quite a bit of background on motivation for these algorithms, why they're good, how you typically implement them. And then for the second part of the talk, I will focus on specifically what we did in Java for the JDK, give some benchmarks and talk about how maybe we can improve this in the future. So first background, I need to talk about side channel attacks. So consider the following code. This may be something in the core of a cryptographic algorithm. You have some non-secret value A and some secret value X, and what you want to calculate is A to the X. This is actually something that you commonly do. And a way that you might do it is you initialize some accumulator R to some initial value, and then you loop over the bits of the secret X. And in every iteration, you square the accumulator, and then you look at some particular bit of this secret value, and if it's set, then you multiply this accumulator times A. And the critical thing here is that branch where you do the multiplication is only taken where the bit is set for some bit in the secret. And the problem with this is that if an attacker can figure out that that branch is taken, then the attacker can learn bits of the secret. And you may think, well, how could he do that? That's just part of the code. And the answer is side channels. And in a side channel attack, the attacker doesn't just see the input-output behavior of some function. He also learns something else by looking at other things that are going on in the system. A very well-known version of this is a timing attack, where the attacker just runs the code and then measures how long it takes to execute. And so if you can measure the amount of time that multiplication takes, then you can trivially figure out how many bits are set in the secret. And there's much more complicated attacks too, where you can do it multiple times and actually figure out the value of each bit just by looking at timing. Slightly more sophisticated attack is a cache attack, such as a flush and reload attack, which is what I'll describe here. And the basis of this attack is that the presence or absence of some program fragment in the cache tells the attacker whether it was executed. So a co-located attacker that's co-located with the victim code could flush that piece of code from the cache, tell the victim code to run, and then look and see if that piece of code has been loaded back into the cache. And by doing that, the attacker knows that code was executed, and therefore that bit of the secret is set. This may seem like a really weird, abstract, theoretical thing, but it's not. It's actually practical in multi-tenant cloud environments where the attacker is on the same machine. It could even be on a different core, but sharing the same cache. And any source of branching, such as if, else, while, the ternary operator, can leak secrets to these sorts of side channels. And for crypto code in particular, there's lots of sources of branching. If you're just doing multiplying numbers or modular reduction, that's usually, you do some divide and conquer algorithm because these numbers are very big. And in general, it's recursive, and it depends, the time it takes depends on basically the value of the numbers. The square and multiply, like I've just said, you'll also see this referred to as double and add, and those are the same thing. It's just notation. A lot of cryptography is based on elliptic curves, and for elliptic curve cryptography, you have to do this point adding operation, where you take some point, you add it to another point, you get another point. And for typical elliptic curve formulas, this works as long as those points aren't the same point, or as long as one of them isn't some special point like the 0 point. And you usually implement them by checking all the points for the exceptional conditions and then only do the add if they're in general position. Otherwise, you have to do something else. And of course, that requires a branch. Indexing is also a problem. There's a lot of optimizations where you do a bunch of pre-computation and you get a pre-computed table. And you look into that table, you look up into it based on the value of some secret. And that, of course, also loads information from the cache, which can be measured and it can use to leak bits of the secret. All right, jump right into some modern crypto algorithms. But first, I want to give a little bit of context just to show what these algorithms do. And we'll consider an example of transport layer security 1.3, which is the latest version of this protocol that you would use, for example, to open up a connection between your browser and your bank's website to communicate securely. And the way that might work, this is a highly simplified form of this, by the way, is that both parties will send a client hello message to each other, where the client will send a key agreement share, and the server will also send a key agreement share. And in this example, only the server is authenticated, so the server will also sign that message to prove that it came from the right person, the right party. The client will then verify that signature to make sure that they are, in fact, talking to their bank. And then both parties will do this key agreement calculation. And the result of that is this shared key that can then be used for much faster symmetric encryption that also can be authenticated, meaning that from then on, the information that they share is secret and also it can't be modified. In Java and the JDK, we have something called the Java Cryptography Architecture, or JCA, also known as Java Cryptography Extensions, or JCE. And this is a provider architecture for crypto services in the JDK. And basically, it's very simple. The API is fairly simple. The application can request algorithms, and then the provider framework looks at the configuration and the environment, and then uses that to choose the implementation. And there's APIs for all the different crypto services that you would need, such as the ones from the last slide: signatures, key agreement, ciphers for the encryption. And this can be used by any Java code, and it's also used by the TLS implementation in the JDK to get these crypto services. And the next slide, I'm just going to jump right into the new crypto algorithms that we're working on for the JDK. So the first one is X25519 and X448, which are new key agreement algorithms. These were delivered in JDK 11 under JEP 324. JEP is the Java enhancement proposal. And, but this is only the JCA only, so meaning applications can actually use this crypto service directly, but it's not yet integrated into the TLS implementation, but we are working on that. Another one that we're working on is EdDSA, which gives signatures using those same curves, currently in development under JEP 339. And the last one that I'll talk about today is Poly1305, which is an authenticator, typically combined with Cha-Cha-20, and when you put those two things, Cha-Cha-20 is a cipher. When you put those two things together, you get authenticated encryption, like what would be used in the couple slides ago. And this is part of the Cha-Cha-20 Poly1305 implementation that was delivered in JDK 11 under JEP 329. This was worked by Jamil Nima. And again, this one is also JCA only. It's not yet integrated into TLS for JDK 11. And there are some other new crypto algorithms that were developed for JDK 11, but they're outside of the scope of this talk. So I just threw a bunch of stuff at you, and you may not be familiar with them, and you may be asking, well, why do we need all these things? Why are they different? We've had key agreement algorithms before. We've had signature algorithms. Why do we need these? And the answer is there's a lot of really nice benefits of these new algorithms. First, that I'll talk about a lot in this talk, is that they're resilient by design against side channel attacks. Other properties, they have very good performance on multiple platforms. The algorithms themselves are more trustworthy in their construction and their selection of parameters. They have very conservative security against known attacks. We've developed a lot of attacks. We in the crypto community have developed a lot of attacks against algorithms, especially public key algorithms in the last few decades. And so all the known attacks, for all the known attacks, they're very secure against them. Another thing, they're also very simple to implement. So people have discovered that the implementation is usually where a lot of the bugs creep in, not the actual algorithm itself. So there's a lot of people try to make the algorithms as simple as possible so you can't implement it wrong. Related to that, there's no need to validate input. This is also something that is easy to get wrong for a crypto algorithm. If you have to validate the input or else something goes wrong, you may forget to validate it, you may validate it wrong, you may validate it in a way that also leaks information. The validation itself could have a vulnerability in some form. Also a nice thing is they're not covered by patents, which is a big deal, especially in elliptic curve cryptography. And all of the algorithms that I mentioned in the last slide and that I'll talk about in the rest of this talk are very important elements of TLS 1.3. They're all optional, but there's only a few algorithms that are allowed in TLS 1.3, so that kind of makes each one more important. So I'll talk a little bit about, next thing is the implementation. So a lot of these algorithms are elliptic curve algorithms, and there are modern techniques to do the elliptic curve arithmetic in ways it doesn't branch. I don't want to get into too much of the math here, but basically when you figure out how to actually do elliptic curve arithmetic, you have to choose a coordinate system, and you have this large space that you can choose from, and there's lots of different ways to do it. So you might as well choose a way to do it that doesn't require you to branch and check for these exceptional points. And also, if you're going to choose a way to do it from a bunch of different options, you can choose it in a way that minimizes the number of multiplications in the underlying finite field, because those are really expensive. And then you can combine that with a branchless double and add loop. So again, double and add is just like that square and multiply loop that I had earlier in the talk. And you can do that by instead of doing an if and then branching, you can just kind of use some arithmetic in there with XOR to just do the same thing every time, but it still ends up conditionally assigning or swapping the value to what you want. It's kind of hard to explain here in a talk, but RFC 7748, which is the standard for X25519, X448, has an example of how to do that. And you can similarly do branchless table lookups. Another thing that you need is branchless finite field arithmetic. And finite field sounds like a really scary mathy thing, but it's really just that you need to do addition and multiplication in the field of integers modulo some value p, where in the case of all these algorithms, p is a prime. And you have typically these constraints, at least related to crypto, is that the numbers are very large, so 100 to 500 bits. It needs to be fast because this operation is the primary bottleneck of all of these crypto algorithms. So for example, X25519, a single key agreement operation, you have to do 2,040 adds and 2,550 multiplications. And these are big number multiplications and big number adds. The value p is fixed and known at compile time, which is actually pretty helpful. It also usually has some useful structure, like what I've shown there, and in a few slides or a little bit later, I'll talk about how you can use that to improve performance. And also the actual arithmetic that you have to do, for example, the elliptic curve arithmetic, only requires 1 or 2 adds before each multiply, which it's not obvious how that would be helpful, but I'll explain later how it can be. So all these algorithms have finite field arithmetic in common. So X25519 and X448 and EdDSA are all elliptic curve algorithms, but you evaluate the elliptic curve on a finite field. Poly1305 is just, for each block of the message, you do a single finite field add and a single finite field multiply. And so it's worthwhile to develop a good high-speed finite field arithmetic implementation that benefits all three of these. And this is kind of a notional diagram of how these things might be organized, and perhaps in an implementation. So each one of these algorithms may depend on some particular finite field. In that box underneath, the numbers are the prime that defines the field. And there may be some specific code for each prime, but there is going to be a lot of common shared code between all of them. All right, so this is where it gets technical, but again, it's just about low-level arithmetic. Let's talk for a minute about how you would typically do big number modular arithmetic. So, for example, maybe you would have an array of 64-bit longs. And if you want to add 2 of these things together, you would just loop through the array, from low order to high order, and then add and carry. And if it's modular arithmetic, you still want to do a modular reduction at some point in there. You could do it at the end, or you can do a bunch of operations and then reduce later. For multiply, you typically use some appropriate algorithm based on the size. If the numbers are pretty small, you can just do grade school multiplication, where you just pairwise multiply all the numbers. For larger numbers, you do some divide and conquer algorithm like Karatsuba. And depending on the algorithm you choose, you may have to reduce during the actual, do modular reduction during the actual algorithm. So I'll show an example. So let's say we have these numbers that are each represented using a 64-bit integer, and each of these little red blocks here is a 64-bit integer, and the high order limbs are on the left. A limb is the typical word for what you'd call one of these things, one of the integers in a larger big number representation. So let's say you had two of these things and you want to add them together. You'd add and carry, and then you'd get one more limb. Of course, it may just have one bit in it. And then when you multiply and carry, you end up with, of course, a whole lot more because multiplication adds a bunch of size to the number. And then perhaps when you're all done, you would reduce. And then you're back to your 4 limbs of 64 bits each. And this is it looks very simple. The problem with this is the carry. The carry, depending on how you do it, may require branching if you're only going to carry, if you actually have something to carry. You can't do it in parallel. You have to start it in the low order and work your way up. And after the add, it's almost unnecessary because you just have to carry that one bit. So it's kind of unfortunate that you take this add operation, which could be fast and could actually be done in parallel, and you make it serial, but just because you have to carry. So let's talk about a better way to do modular arithmetic. You can still use 64-bit longs, but you can store fewer bits in each limb. And what that means is you have a little extra space that you can use to kind of cheat in some ways. So for example, for adding, all you have to do to add 2 of these things is you just loop through the arrays and then add. You don't have to carry, you don't have to reduce, because you have extra space, and you can just accumulate the extra information in that extra space in each limb. For multiplication, again, you can still do something simple like grade school or multiplication, followed by a carry reduce. A typical way to do this is, the platform will have a 64 to 128-bit multiply operation that you can use. And then, you'd reduce back down to smaller values. And this does also work with divide and conquer algorithms like Karatsuba, but it's usually only worth it for larger values like 400 bits or so. And a big way that this improves performance is because now adds are cheap. You can just do them very quickly. You don't have to carry or reduce during them. So let's show an example of this. So in this representation, this is actually a typical representation that's used for curve 25519, which is used for X25519 and EdDSA with this curve. So in this representation, I have 5 limbs, and I store at most 51 bits in each 5 limbs, but the limb itself is 64 bits. So that red space is the space that's actually occupied by information, and the blue space is the free space that I have to work with. So to add, if I have 2 of these, I want to add them together, I can just add them, and I can accumulate 1 more bit at most in each position, and that's not a big deal. For multiplication, things do get a little bit more complicated. Again, I'm using the 64 to 128-bit multiply, so now I have much more limbs, and now they're 128-bit values, but they have at most 108 bits in each limb. But I do still have a little bit of space that I can work with. And so I can reduce that back down, and now I'm back down to 5 limbs with only 60 bits each, so I'm losing a little bit of space as I go, and as long as I don't run out, I'm fine. And I can use the remaining space for my carry reduce sequence that gets me back to where I started. So in this example, you carry out of the high order limb, reduce back in to the rest, and then just do a full carry through all the limbs, and then you're basically back to where you started, 51 bits and 5 limbs. It does look way more complicated than it is, but it's also much more efficient. Also important for efficiency is you have to be able to do the modular reduction efficiently, which is something that's done at the very end of the sequence or the chart that I just showed. What's really helpful is that modern algorithms use very well-structured primes that make this easy. So for example, here are the 3 primes that are used for curve 25519, curve 448, and Poly1305. They just have a few terms in them. And if you represent your array of limbs in just the right way, and things are aligned right, then reduction can be done very simply. You just have to do 1 multiply and 1 add for each additional term. So for example, to reduce in the curve 25519 field, you take a high order value, multiply it by 19, and then stick it in the position 5 spots earlier, and then set that limb to 0. Leave it as an exercise to the reader why that's correct, but that's all you have to do, and it's very simple and of course very efficient. In general purpose reduction, you have to do something much more complicated. Again, it's kind of like a divide and conquer sort of thing, which actually depends on the value. So I'll finish up with some finite field implementation notes. So in the implementation of this sort of thing, you do have to specialize the implementation for each field. So for each field that you want to work with, you have to decide how many limbs, how many bits per limb. how to reduce using the structure of the prime, and then also the carry reduce sequence that you perform at the very end depends on how much space you have left over. So sometimes you have to tinker with that to get the best one. But a lot of the implementation can be shared. So the add and the multiply, the carry, the input and output conversion, that's all the same between all the fields. And after all this, very importantly, the implementation doesn't branch. So you always carry and reduce after the multiplication regardless of the value. You never actually look at the values. You just make sure that no matter what the value is, everything's going to be OK. All right, so that was all kind of general stuff, general implementation techniques that have been used by lots of people in the applied crypto community for a while now. And in the next part of the talk, I'll talk about how we adapted this to Java to implement this in the JDK. So Java has some challenges that you may have thought of when you're reading some of the last slides. The first one is that, well, of course, there's no 128-bit types in Java. We have 64-bit longs. And we don't really have direct access to that 64 to 128-bit multiply. Another limitation, we don't have an API for AVX, Intel AVX and SIMD instructions, which is you know, instructions on the processor that will allow you to do, for example, 4 multiplications at once. There is some auto-vectorization in the JDK, which is actually very nice. So if you have relatively simple things, the JIT compiler will auto-vectorize it for you. But unfortunately for these crypto algorithms, the stuff that you have to do to make this work is actually not trivial, and it's not the sort of thing that you could expect the compiler to do. So you need an API for it. Another thing that Java doesn't have is precise register management. I'll talk about that more in the future, or in the later slides. And also full support for unsigned arithmetic, which is kind of a minor thing, but it does factor in. Still, with all these challenges, the performance of these algorithms is pretty good. It's fast enough for typical applications. Of course, it's slower than the fastest native implementations. And we can't take full credit for this. A lot of this has to do with the fact that these algorithms are just easier to implement efficiently on any platform. So a very quick overview of the solution. I didn't have a lot of choice in how to implement the elliptic curve operations. They're all the RFCs that standardize these algorithms say exactly what to do, so we just did exactly that. Something that helps quite a lot is use mutable objects to avoid garbage collection and copying. And this is something that, of course, it complicates things. We all like immutability, and it makes things easier to understand. But for low-level tight loops, you expect a lot of the compiler, the JIT compiler, to optimize that for you. And if you really want to guarantee good performance on all platforms, using mutable objects and reusing them is a pretty good way to get that. Because we didn't have the 64 to 128-bit multiply, we used the 32-bit representation, so we only need the 32 to 64-bit multiply, which of course we have. We also use signed arithmetic because this is, there's better support in Java for it. Some parts of the code had to be hand optimized. So for example, using mutable objects and reusing them. There's also something I'll talk about later. That there was one example where I had to use individual longs instead of arrays in the field arithmetic to get really good performance. And I also want to note that if you look at the code in the JDK for this, that the solution balances performance with maintainability. There are some cases where there were ways to do it that may have been slightly faster, but it's also worthwhile to just have something that's nice in general and works for everything, maximizes code reuse, and so there were some decisions like that went into play also. Okay, the implementation of the finite field for these algorithms is there's the number of limbs and bits that I use for each one in case you care about this. All of these are pretty standard. They come from the various academic papers on these topics, with the exception of curve 25519, in which the representation is a little bit unusual because it's not aligned exactly with the prime. But the nice thing is it makes it more general and simple and more easy to reuse for other fields. So I also use signed long values in the representation. So in this example here, if you wanted to represent the number 9 mod 11, you could represent it as a 9, or you can represent it as a -2. And I represented it as a -2. And it's there's not a huge benefit to doing that. It complicates the carry operation a little bit, but it makes the subtraction simpler. but it's kind of a wash. But the real motivation behind that is because Java just has better support for signed operations, and I didn't want to run into a situation where we had a signed version of some operation, but not an unsigned version. So I used a signed representation. And after all of this, this implementation is branch-free, and for the purposes of these algorithms like X25519, it's 10 times faster than big integer, which of course makes a huge difference. Something that surprised me a little bit during this implementation process is early on I had a loop that looked like this, this is for the main multiplication loop, so I have this array C that stores this kind of intermediate value, and then I loop through these two input arrays A and B, and I just do the pairwise multiplication of them. This is the grade school multiplication algorithm. And then once that's all done, I reduce C into a smaller output array. And you can see like all of these, the number of limbs here is all constant. Everything in here is constant. The compiler possibly could be able to figure out that array C doesn't escape and that everything is constant, and then you can just unroll everything, and that you won't use temporaries, you won't do all the array index calculations. But unfortunately, at least at the time I tried this, the JIT compiler did not do this. So I addressed this problem by just manually unrolling it myself, resulting in kind of ugly looking code where I just, use individual long values instead of an array. And it's ugly, but it's worth it because it doubles the performance of the X25519 operations. And this was actually found by Sergei Kuksento on the Java performance team. Okay, now after all that, let's see how the performance is. So an overview, I'm going to share a bunch of benchmark results. These are all tested on this laptop, in fact, with a Core i5 at 2.4 gigahertz. The tests were run in an Ubuntu VM on a Windows host, and all the useful hardware acceleration was enabled. So it does have, I compared to AES in one of these, so I have the AES instructions turned on. And I'm only testing and reporting implementations in the JDK just to give a rough comparison of what our performance is now to what it was in the past for similar algorithms. And so you should use this to kind of get approximate relative performance only, but not absolute numbers. So let's start with X25519 and X448, and let me explain the chart a little bit. So those first three bars in each chart are P256, P384, and P521, which are elliptic curves that have been in the JDK for a long time. And they're implemented in C code, in native code. And the next two bars, X25519 and X448, are the new curves that I added for in JDK 11, and this is for key agreement. And each of these has a different level of performance and also has a different security strength. So for example, the first curve, P256, has about the same security as X25519, and those are the ones that you should compare. And so you can see that at roughly the same security strength, X25519 is about 5 times faster than P256. And that performance continues along for X448. It's harder to compare directly because the security of X448 is in between those other two curves, 384 and 521. But the relationship holds up. It's 4 or 5 times faster. And again, I want to stress that we're comparing a Java implementation of X25519 and X448 with a native implementation of 256, 384, and 521. So that's a pretty good result, I think. But of course, not pictures. The fastest native X25519 implementations on this machine would be around 15,000 operations per second. So we're still 4 or 5 times faster than the best we could be if we were using a pure native implementation with using SIMD, AVX operations, and all that kind of stuff. So the picture for EdDSA is pretty good. Not quite as good because EdDSA is just, it's not as fast as X25519 just by the nature of the algorithm. And so this is a signature algorithm, so I'm comparing the generate key pair operation with the sign and the verify. And sign and verify is a little complicated because there's also, you have to hash the message before you do the computation, and so this benchmark is complicated by that a little bit. So the best thing to look at is probably the generate key pair operation. And again, we still have the same curves that we start with, 256, 384, and 521, and we're comparing them with the ED25519 and ED448. And so we can do the same kind of comparison. So P256 has roughly the same security as ED25519, and it's about the performance is about twice as good, at least for generate key pair. Again, with sign and verify, it's complicated. And similarly for ED448. Poly1305 is a lot harder because I don't really have anything to directly compare it to. It's an authenticator kind of like HMAC SHA-256, which I put on this slide also, but it's a one-time authenticator versus HMAC, which is not. So it's tough to compare exactly, but just to give you a rough idea of its performance. So that first bar is HMAC with SHA-256, and the second one is Poly1305. So you can see it's about twice as fast. When it's used as part of an authenticated encryption algorithm, it's even more complicated. So that third bar is AES-GCM, which is by far the fastest authenticated encryption algorithm on the JDK. And the bar after that is CHA-20 Poly1305. And you can see AES-GCM is much faster, but it's kind of an unfair comparison because AES-GCM is not only in native code, it uses AES instructions on the CPU, which we don't have for CHA-20 Poly1305. So it's tough to compare, but I do think that the performance of CHA-20 Poly1305 is still pretty good. So let's look to the future a little bit and see if can we. I mentioned we still have quite a gap between the fastest native implementations, and how could we possibly can we close that gap, or do other things that improve performance? The first thing is better code generation. This isn't so much about performance as it is about those ugly hand unrolled loops that I mentioned a while ago, where I had to take a for loop and just change it into a bunch of long values with assignments for each one. It doesn't seem really necessary. It seems like a really smart compiler could figure out that you don't have to, that it could optimize all that so you don't have to hand unroll it yourself. But it just takes a lot to figure out you have to figure out the array doesn't escape, everything is constant, the loop can be unrolled, all that kind of stuff. So the Graal VM developed by Oracle Labs will actually do that. And this was an experiment by Eric Caspel on the Java performance team determined this. And so if using that VM or a similarly powerful VM that can figure out this optimization, then we could just use the simple for loop in the code, which doesn't help with the performance at all, but it does make it more simple and easier to maintain. What would help the performance is if we had better low-level instructions, and there's a couple different things that may help here. So if we had the 64 to 128-bit scalar multiplication operation available, and I could use it in the Java code, then I could use half as many limbs in each representation, and everything would be quite a bit faster. So there is an intrinsic for this that was added in JDK 10 that does part of it. So it's for math.multiply high, which multiplies two 64-bit numbers and gives you the high-order 64-bit result instead of the low-order 64-bit result. And so in theory, the compiler could combine that with the actual primitive multiplication into a single operation. And this is actually, honestly, this is something that I think I just need more experimentation with to see how well that could work. Also useful would be API for SIMD, like Intel AVX. So if really the best implementations of X25519 in particular use this approach, and they do several 32 to 64-bit multiplications in parallel. There is some work on the Panama project, which is an OpenJDK project that is working to develop a vector API that would give access to all of this. And I mentioned before that the things you have to do for this particular code to use SIMD is not at all trivial. But I was able to develop a prototype for X25519 with the Panama vector API that matches exactly, that does the exact same thing that the best implementation does in this area. And the performance isn't quite there, but I think with a little bit more work, it probably could get close. Another thing that this isn't something that I expect Java to improve in the future, but it's really more of a limitation that perhaps I don't know, perhaps we just have to accept, is that really the best low-level crypto algorithm implementations, they can't even use C code. They use assembly code, and that's because they need really precise register and memory management. And a good example of this is for Poly1305, which minimizes the amount of register use so it can fit the entire operation into registers, which of course makes it very fast. So for example, in Poly1305, you have 3 to 5 registers for an accumulator, and you have another 3 to 5 registers for this fixed R value, which you calculate at the beginning. It's part of the secret key. And then from then on, the only thing you have to do is read from memory, do some calculation in registers, and then update your accumulator in the registers. And then you only write out at the end. And so, of course, this is really fast. You can also do other things like store information in floating point registers and then use all the general purpose registers for the cipher. And so now you've done your entire authenticated encryption operation without ever going out to memory. So obviously in Java, we don't have anything like that low level, but again, not even in C. Conclusion. So we have implemented some modern crypto algorithms in the JDK, and there's more on the way, and the performance is definitely good now and perhaps could even be improved in the future. For more information, here's links to all the JEPs, or you could just search for them for the different algorithms involved. You can also try it out in the JDK 11 release. The JEPs have example code that you could use to actually try all these algorithms out. I do want to recommend a few other sessions. So there was the Transport Layer Security 1.3 session, which unfortunately happened in the past in this room. So if you missed that, I would suggest, and you're interested in this topic, I would suggest you look up the slides for that. Sergey Kuksenko, who I mentioned this talk, who is really good with performance stuff, is giving a couple other talks here related to performance. First about HTTP2, the new HTTP client, and another one about garbage collection. And if you want to learn more about cryptography in the JDK, you can come to my Hacker Garden tomorrow morning at 10 o'clock. And that's all I have. Are there any questions? Yeah, use the microphone if you would. Thank you.
So sorry, I get the words. You threw a lot of stuff at us. I'm trying to look back.
Yeah.
This is more of a sort of a geeky interest question. When you were talking about your signed modular representations.
Mm-hmm.
Are you always pivoting around zero? I'm not using the right term. Do you have a single standardized representation? Do you always use a negative for the high end and a positive for the low end?
Yes, I do. I agree. It's a geeky interest question, but it's a great one. I love it. Yes. So during the carry operation, so during the input conversion, you have usually what I do is I just store everything unsigned, and then I go through and I do that pivot, like you said, to kind of make everything the right thing. And you have to do the same thing on the carry operation. With the exception of Poly1305, in some cases I don't bother, just because that representation is so roomy, so you can store. Excuse me, you have extra space in that representation, so you can store the unsigned value, and you don't have to worry about kind of making everything small enough. So for the most part, the answer is yes, but I also cheat sometimes because I can sometimes. And a lot that just comes down to how much space there is and if I'm going to run out of it before the end.
That makes sense. When you mentioned it, I was thinking, well, of course, for modular representations, those two are completely equivalent.
Right.
Except if you actually have to do any sort of comparison.
Right.
Thank you.
Yeah. Any other questions? Okay, thank you.